السلام عليكم ورحمة الله يعطيكم العافية. Today we will talk about the vectoral analysis of ECG and ECG interpretation, which are the last topic of the cardiac physiology. So our main objectives of this lecture to recognize the normal ECG tracing, also to draw the hexagonal axis of the ECG, and to find the mean electrical axis of the QRS complex. Also, we will look at the vectoral analysis in the first three leads, how to draw the vectors for each lead. Also, we can have a look at how we can calculate the heart rate from the ECG tracing to determine the rhythm, and to calculate the length of intervals, and to see a few of abnormalities that we can figure out from the ECG tracing. The main principle of vectoral analysis of ECG is that the main current of the heart flows from the area of depolarization, okay, to the area of polarized, okay, parts. So from depolarization to polarized areas. And as we discussed before, this graph shows the negative, okay, charges that are on the surface, okay, which means we have positive inside the cells. The beginning of depolarization, we all know that it starts with positive charges in the inside of the cells. And so these are this is the area where depolarization starts, okay? And the surrounding area with positive sign, it is actually a surface charge. So inside of the cells or of the heart muscles, we have negative charges here, okay, representing polarization status or resting membrane potential, okay, in these areas. And actually the main vector, okay, of this current or of these potentials is running, okay, to the inferior and to the left side, okay, which we called mean vector through a partially depolarized ventricles. So this is partial depolarization, when almost half of the ventricles are depolarized and half is polarized, still in the rest membrane potential. And by convention, this arrow, the arrowhead, is pointing toward the positive direction. The length of the vector, okay, represents the voltage of the potential. So the more voltage of the potential, the longer the vector, okay? So if we have seen a small vector, that means that the potential or the voltage of the potential is small. So the potential generated at any instance of time can be presented by a vector that we call instantaneous vector, mean vector. So at any instant, okay, we can have a vector. So we can have many vectors. Each instant we can have a different vector than the next instant, okay? So any vectors of these we call instantaneous mean vector. So at that instant, this is the mean vector, okay? Now the normal mean QRS vector, when the heart is actually depolarized or partially depolarized, we get the normal mean QRS vector, which is has an angle of about 60 degrees, okay, from the horizontal axis. And this is the mean normal cardiac mean vector, okay, represents the cardiac mean vector, and the angle from the horizontal plane is about 60 degrees. Again, this is the Einthoven's triangle that we talked about in the last lecture when we talked about the bipolar limb leads 1, 2, and 3. And you can see here lead 1 from right arm to left arm, and lead 2 from right arm to left leg, and lead 3 from the left arm to the left leg. If we wanted to put these lead axes in a circle where we can see or place these axes with angles that we will put each lead in the center of the heart, okay, and keep the exact angle that is found in the Einthoven's triangle. So lead 1 will stay horizontal if we put it or extend it from the center of the heart, so the angle is going to be 0. For lead 2, if we moved it from here and put it in the center of the heart, okay, then the angle from the horizontal is going to be positive 60. And by the way, any angle below the horizontal line is going to be positive, or if we go clockwise from 0 to the lower part of this circle, it's going to be a positive angle, okay? But if we are going or extending these vectors in the upper side, okay, if there is any lead axis that we have to put in the upper side, then the angle is going to be negative. Okay, so here all of the 3 lead axes, 1, 2, and 3, let's talk about 3. We will just move it from here and just put it starting from the center of the heart. The angle is going to be 120 and positive, okay, because it's in the lower side or half of the circle. So all of the 3 leads have positive angles. This is what we call axial reference system, okay? And this is actually trigonal. We call this trigonal axial system, okay, because it's composed of 3 leads. Now, again, this is the mean cardiac vector, okay, where it represents the cardiac axis, okay, through a partially depolarized ventricle. You can see that the vector is long because half of the ventricle is depolarized and the other half is polarized. And the direction is to downward and leftward. So in the axial reference system, the axis of lead 1 was 0, okay, because it lies exactly in the horizontal direction of the right and left arms. The axis of lead 2 was positive 60 degrees because the right arm connects to the trunk or torso in the top right corner, and the left leg connects to the trunk in the bottom left corner. The axis of lead 3 had a 120 degrees positive because it's in the lower side. Looking at the 3 other leads, okay, limb leads, which are the augmented unipolar leads, we have the AVL, as you recall from the last lecture. The AVL here on the left arm, okay, and the center or the negative electrode is in the center of the heart. AVR, okay, from the right arm and the center negative electrode in the center of the heart. And the AVF extends from the center of the heart, and the positive is in the bottom or in the pubic area, okay. If we want to see the angles of these leads, you will see that AVL, okay, has an angle of 30, but because it is in the upper, okay, side of this circle, okay, in the axial system, it's going to be minus 30 degree, okay. For the AVR, okay, from the horizontal axis, okay, to the lead axis, there is 120 and minus because it's also on the upper side of the circle. So it is about 180 minus 30. That's when we get 120, and it's minus because it's in the upper half of the circle. Now for the AVF, okay, you can notice that the angle, because it is perpendicular to the horizontal, okay, line or horizontal axis, it is positive 90, and positive 90 because it's in the lower half of the circle. So we can put all these 6 leads together, okay, the first 3, the lead 1, 2, and 3, and the AVL, AVR, AVF together, and you will see how they relate to each other, okay, in this graph. We have 2 leads that are in the negative, okay, side of the circle, and the other 4 leads are, or 3 leads in the positive, and 1 horizontal, which is lead 1. So AVL is here, okay. It actually bisects the angle between lead 1 and the extension of lead 3 here, okay. So it's going to be minus 30 because it's in the upper half of the circle. For AVR, okay, it actually bisects the angle between the extension of lead 2 and the extension of lead 1, so here, okay, and the measurement of this angle is minus 50, 150 or 150, or 180 minus 30, okay, 180 minus 30, it's going to be 150, and it's minus because it is in the upper half of the circle. For AVF, okay, because it's in the lower half, it is positive, the angle is positive, and because it is perpendicular to the horizontal line, it's going to be positive 90. And so it's not only perpendicular to the horizontal line, but also bisects the angle between 2 and 3, okay, and that's why we get AVF angle of positive 90. So if we can have a further look, you will notice that lead 1 and AVF are perpendicular to each other. Lead 2 and AVL also should be perpendicular to each other. Lead 3 and AVR also should be perpendicular to each other. So in the vectoral analysis of ECG, we place all the leads vectors, okay? So we can put the 3 bipolar leads and also the augmented leads all together, okay? With their angles as we talked previously. And this is another way to put leads with the AVR, AVL, AVF, the bipolar and the unipolar leads, okay, in order to make it easier for you to memorize the angles and the relationships between these leads. You can memorize how are they, how we can put them in a triangle, and then how can we measure the angles in the axial reference, okay, or axonal reference system. Now let's talk about how can we determine the mean electrical axis. Okay, how can we determine the mean electrical axis of the heart? Okay, so this is a demonstration of how can we do that. We get the ECG. Okay, we take two leads, two different leads. For example, here we have taken an ECG of lead 1, and from the same ECG we took the lead 3. Now, from lead 1 we will measure the sum, the algebraic sum, okay, of the height, okay, of the positive and the negative of the QRS complex. So if we have a positive deflection, we measure the length of this, how many small squares, okay, and if it was positive deflection, we put the positive sign. For the negative deflection here, okay, we put a negative sign here for the Q, which is here minus 2.5 small square, and the R was positive 16, and we sum the positive 16 and the negative 2.5 to get positive 13.5. So this is the algebraic sum of the height and the positive deflection and the negative deflections of the QRS. In lead 3, you can see that there is a positive deflection that has a height of positive 14, okay, small squares, and the S is minus 5 small squares, so the algebraic sum is positive 9. I say here small squares, but you cannot see them actually on this, because each big square of these have small squares that don't show here, but on your ECG you will see that. Okay, so the sum here is going to be positive 9. So this is actually the sum or the average for first lead and the average sum of the third lead. Okay, now we put the leads, okay, in the axonal reference system, lead 1 and lead 3, as we know. Lead 1 here on the horizontal, and lead 3 is has, as you know, a positive 120 degree here. Okay, so this is the place of lead 3. Then for lead 1 we have an average of 13.5, so we put a point on 13.5 of small squares on the ECG. Okay, and on the lead 3 we have positive 9, so we put here, we count 9 squares, okay, and in the positive side, of course, okay, and then we draw a point here, a point here. Okay, after that, okay, we draw a perpendicular line, okay, going down from the point on lead 1 that we put a mark on it, and then a perpendicular line from the positive 9 point, okay, downward until they intersect. Okay, here is the point of intersection between the two perpendicular lines to the leads. Okay, now this intersection actually remarks the axis of the heart for this ECG. So we just draw a line from the center here into the intersection, and we measure the angle. Okay, we measure this angle, and here it is 58 degrees and positive. So this is the cardiac axis of this particular ECG. This is another example of how we can calculate or measure the angle of the axis of the heart, or the cardiac axis. So we can take two leads, any two leads, but it's easier to take two leads that are perpendicular, which are here lead 1 and lead AVF. So we take the ECG, look at the lead 1 and lead AVF QRS complexes, okay? We look at the length of R, Q, and S waves, and we sum or do the algebraic summation. Okay, we can count the number of small squares, and please take care of the positive and negative signs of the waves. If the wave was on the upper side of the line, or it is an upper deflection, we put positive sign. If it was lower deflection, we put negative sign, and then we sum. We have the sum. Okay, we sum them together. So if R was, for example, 14 small squares, positive, and the S is 4 small squares, but in the negative direction, so this should have a negative sign. And if Q was 3 SS, also down deflection, will have negative sign, then the total is 14 minus 4 minus 3. And so it is going to be positive 7. Okay? So this is for lead, doesn't say which lead here. Okay? So this is for lead 1. Okay. If in lead 2 was also the sum was 7 small squares, so this is the example. In lead, here 7 small squares for lead 1, and the sum, algebraic sum for lead AVF was also 7 small squares. Then we draw this, we put a point on the lead 1 and axis, and on lead AVF axis at 7 small squares. And then we draw a perpendicular line to the lead axis. So here is the perpendicular line. Let me show you the, okay, so this is a perpendicular line for lead 1. Okay, it runs through the point of 7 small squares down. Okay, and then from lead AVF, a perpendicular line that goes until it intersects the first line. Okay, so at the intersection, we draw a line that passes through the center of the axonal reference. Okay, this is going to be the cardiac axis. Okay, so this is the cardiac axis, and either by measuring the tan of this angle, or by measuring the angle, okay, directly measuring the angle using the mathematical tools to measure angles, okay, we can know what is the angle of the heart, and it's going to be positive because it's in the lower side of the circle. Remember, the lower side below the horizontal line, all angles are positive, or we can say clockwise direction have positive angles, but if you go anti-clockwise, it's going to be negative angles. Okay, so here we use the tan, okay, of the angle, which is tan opposite, okay, over adjacent, okay, the length of the opposite, and we divide that by the length of the adjacent, and then we can get, using the calculator, what is the angle, and here it is 45. Okay, so the angle of the axis of the heart is 45. Normally, we said that in average, in most normal cardiac axis, it is about 55 or 60. Now, this is another example. How can we plot the mean of electrical axis from the heart from two electrocardiographic leads? So, here we have lead 1, okay, we have also lead 3, and we know the length of lead 1, lead 3. We measured that. We can measure that. We can measure the length of the wave, the algebraic sum, okay, of the height and the depth. And you know that this is the axis of lead 1, and lead 3 is, as you can see here, it is positive 120, the angle. Between 1 and 2, it's 100 and positive 20. Okay, so you put the vector or the lead 1 vector here, okay, and the lead 3 vector, which is you can see here, it's the length that we measured in the sum, algebraic sum in lead 3, and then we draw perpendicular lines, okay, and then we can draw the axis, okay, in the middle here, running through the intersection, okay, like this. Then we can know the angle here. Okay, so this is going to be the cardiac axis. Or mean electrical axis of the heart. Another example here to measure the cardiac axis angle. We have here lead 1, lead 3, and we measured the Q and R. Here is positive 4.5, and here is positive 22. Okay, so the same thing, we draw perpendicular lines from the two leads, and then at the intersection we draw a line that passes through the intersection from the center, and this is going to be the angle, okay, of the cardiac axis, and it's here positive. Again, the angle is here positive. Another example here that shows an ACG. We got two leads, lead 1 and AVF lead. The AVF lead, the algebraic sum was negative. That's why we drew here the mark here on the negative part of the axis, vertical axis. And for lead 1, it was positive. So we drew perpendicular lines, okay, and then we drew a line that intersects or passes through the intersection between the two perpendicular lines. So this is the mean cardiac axis. Notice that this cardiac axis is deviated from normal. We expect the normal to lie between 0 and positive 90, okay? But in this case, it is deviated from the normal. And because the angle lies between 0 and minus 90, we call this left axis deviation or left cardiac axis deviation. Okay, and now we will look at those are the probabilities of cardiac axis angles that we can get from a patient's ACG. This is the normal mean electrical cardiac axis. The angle is between 0 and positive 90. Okay, so if it was here, this is normal mean electrical axis. Okay, downward to the left. But if the angle was between 0 and minus 90 here, this is what we call left axis deviation of the QRS. Okay, so the axis is deviated to the left, or left axis deviation. If the angle was between positive 90 to positive 80 here in this quarter, okay, so this is a right axis deviation of the QRS. So the axis is deviated to the right. The angle is between positive 90 and positive 180. So the less probability is to get an angle between minus 90, okay, and between 180, okay. So this is actually what we call severe axis deviation. It could be right or left, and we can determine that from knowing which part of the heart has the disease. If it was right side, it is right severe axis deviation. If it was left heart disease, so it's left severe heart axis deviation. Okay, so here are some rules if you are using lead 1 and AVF to determine the cardiac axis, which is an easy way to do that. First, if you have the algebraic summation of lead 1 and that was positive, plus the algebraic summation of AVF was also positive. So here is the summation of lead 1 was positive and the summation of AVF was positive. So the cardiac axis is going to be right here in this corner, and this is the normal range. Okay, but if the algebraic summation of lead 1 was positive, so in this side, but the algebraic summation of AVF was negative, so at this side, so in this corner, that means the electrical axis is between 0 and minus 90, and that is a left axis deviation. That's when we have a left axis deviation. And if the algebraic summation of both AVF and lead 1 were negative at the negative sides, okay, so that means the cardiac axis right here is right here in the right axis deviation corner. Okay. Finally, if the algebraic summation was negative for AVF, okay, and negative for lead 1, so that means the cardiac axis is between the angle minus 90 and 180. Okay, so then here it's going to be an extreme cardiac axis deviation, either left or right. So according to the heart disease, we decide if it's right, extreme right, or extreme left axis deviation. Now let's walk you through the principles of vectoral analysis of the ECG. And first, before we start drawing an ECG from 3 leads, okay, during the different phases of ventricular depolarization and repolarization, we will look at the main principle of determining projected vectors in the different leads, okay, from the cardiac axis or the main cardiac vector. Okay, so in this graph, okay, in this the trigonal, okay, reference system, axonal reference system, we have the lead 1, lead 2 axis, and lead 3 axis. In this corner we have the cardiac axis, okay, and it's called A here, okay. So A represents the main cardiac axis, or what we call instantaneous, okay, cardiac axis. Okay, so this is the cardiac axis, so this is what is really the vector representing the electrical potential, the instantaneous electrical potential in the heart. But we need to know how does each lead, okay, see that vector. Okay, so each lead will see that vector in a different way. How can we determine that? We can determine that by drawing a perpendicular line to the lead from the arrowhead of the instantaneous cardiac vector. Okay, so then we will get projected vectors on the lead. Okay, so B is the projected vectors, okay, of the heart in lead 1. Okay, this is the vector that you will see on lead 1 for the cardiac axis. And for lead 2, we also will draw a perpendicular line on lead 2 from the arrowhead of the instantaneous cardiac axis. So this is going to be the projected vector on lead 2 for the instantaneous cardiac axis. And for lead 3, at this moment, if you write or draw a perpendicular line on the lead 3, okay, from the cardiac axis, from the instantaneous cardiac axis, then this is the projected vector on lead 3. Okay, so the projected vectors in different leads, they don't have equal, okay, length, okay, because it depends on the perpendicular line that we draw and the angle of that lead. So it's exactly as if you are looking at a certain object, but from different angles. You look at that object, it is the same object, but you look at it in different angles, so you get a different view of that object. And that's what's happening when we use different leads for ECG. اوكي. الفكرة انه احنا بالاي سي جي بنحاول انه نطلع على الالكتريكال اكتيفيتي اوف ذا هارت في كل لحظة، اوكي، في كل انستنت، لكن من زوايا مختلفة. اوكي، كيف الزوايا هاي المختلفة احنا بنحصل عليها؟ عن طريق placement of electrodes اللي هي بنسميها إلها طريقة معينة بالوضع، وبالتالي إلها axis أو محاور مختلفة، فبالتالي بتنظر إلى الهارت أو بتلتقط صورة للإلكتريكال أكتيفيتي من زوايا مختلفة. أوكي، هاي الفكرة الأساسية من الليدز المختلفة، إنها هي عبارة عن زوايا مختلفة للنظر إلى القلب. اوكي، وبالتالي احنا بنكتشف هون اذا في اي مشكلة في جزء معين من الهارت، اوكي، بنشوف في خلل في 2 من الليدز فبنعرف، او 3 من الليدز، فبنعرف انه في مشكلة في هذا الجزء اللي هدول الليدز متخصصين في انهم يلتقطوا صورة او زاوية من هاي الليدز. اوكي، so let's apply this principle on drawing an ECG, okay, in the first 3 leads, bipolar limb leads, okay, during the depolarization phases of the ventricles. Now let's apply the vectoral principles on drawing an ECG, okay, during the different depolarization phases in the heart. And we will start with the beginning of depolarization, and the depolarization starts in the septum here. So this is an image representing the heart going at the first let's say instance of depolarization. This is the time point of 1, okay, seconds after onset of depolarization. You will see that the cardiac or instantaneous cardiac vector is actually lies in the cardiac septum, and it is still short because only a small part of the ventricular septum has been depolarized. Okay, so we move this vector, the instantaneous vector, to the trigonal, okay, of the 3 bipolar limbs leads, and this is how we draw them: lead 1, lead 3, and lead 2. So we draw the cardiac axis exactly as it looks here in the heart, and downward, it's downward, okay, and inferiorly looking to the inferior side, so we just move it to the axonal reference, and then we will see how does each lead, okay, of the three leads will see that vector, or will look at that vector. So for lead 1, we draw a perpendicular line from the instantaneous vector to lead 1. So the perpendicular line will have a 90 degrees, okay, with lead 1. And after drawing that, okay, you will see the length of the projection, okay, which is going to be an arrow on the lead 1. This is a small, okay, or short, and we call it projected vector, okay, projected vector in lead 1. So this is how lead 1 sees the instantaneous cardiac vector. So because it's going to the positive lead, moving to the positive lead, it's going to be a positive deflection, but very small, okay, very small. So this is how is it drawn in the ECG. Depolarization in the ventricle will start like this in lead 1 at this instant, of course. Now for lead 2, we also write or draw a perpendicular line to lead 2, okay, from lead, of course, from the instantaneous vector to lead 2, and we look, they are very close to each other, so it's hard to see the the difference or the distance between them, but you can clearly see that the projected vector on lead 2 is very long, and it's actually almost equal to the length of the cardiac vector, instantaneous cardiac vector. So it's going to be positive also, okay, because it's moving along with the cardiac axis, not away from the cardiac axis. Okay, so as you can see here, it is actually going to be a positive deflection that is longer than the in lead 1. Why? The length of the ECG drawing, okay, it's actually proportional to the length of the vector, the projected vector. Okay, so because lead 2 sees more of the cardiac ventricular axis or instantaneous axis, it will draw a longer line. Okay, and it's positive because it is along or with the direction of the cardiac axis. Now, for lead 3, we draw also a perpendicular line going down from the instantaneous cardiac vector to the lead 3, and this is going to be the projected vector in lead 3, and it's going to be also, okay, positive because it's going to the positive direction, and as you can see here, it is also a positive deflection that is a little bit shorter than what is there in lead 2. Okay, so all these electrocardiographic voltages, okay, are low because the depolarization is still partly or very small part is depolarized. The voltage of lead 2 was greater than the voltages in lead 1 and 3. Why? Because the heart vector, as we said, is more parallel and extends mainly in the same direction of the lead 2. They go parallel to each other, so the perpendicular line will be actually will make the projected vector longer. Okay, so this is the first instance in the depolarization of the ventricles. Now in the 0.02 second after onset of depolarization, you will notice that much of the ventricles or ventricular septum and part of the ventricles, a good part of the ventricles, has started depolarization. So the cardiac vector is longer, the instantaneous cardiac vector is longer. Okay? So now let's see the projections on the three leads. Okay, so we will just move the cardiac vector as is to the trigonal reference, okay? And then we will draw projected or perpendicular lines to get the projected vectors in the three leads as we have done in the previous slide. So this is the projected vector for lead 1, this is the projected vector for lead 3, and this is the projected line for lead 3. You will notice again that the line, okay, the positive deflection line is going to be longer in lead 2 and a little bit shorter in lead 1 and in lead 3. But in all three, we will have a continuation of the positive deflection on ECG in these three leads. So the electrocardiographic leads, they have increased because the voltage has increased. Okay, the amplitude is increasing as the voltage is increasing because much of more areas of the ventricles have been depolarized at this moment, and lead 2 was the largest. Okay, as the mean vector is now 60 and it's very parallel or in the same direction of the lead 2. Now in this phase, in about 0.35 seconds after onset of depolarization, you will notice that the heart is getting almost most of the areas have been depolarized. Okay, so the vector is getting shorter because we are close to having complete depolarization. So whenever we are close to complete depolarization, the voltage gets shorter and shorter. Okay, so the vector has started to get shorter than the maximum length that we have seen in the previous picture. Okay, so we will move the instantaneous cardiac vector to the axonal reference and draw perpendicular lines to see the projected vectors in the three leads. And how is it going to be drawn by the ECG three leads? Okay, so first for 2 or for 1, let's start with 1. This is the perpendicular line to lead 1, and this is the projected lead 1 vector of the cardiac axis, and this is for 2 and this is for 3. So it's longer in lead 2 and it is a positive because it's in the positive sides of the axis. So we will draw positive, okay, wave, but because it's getting shorter in amplitude, we are going down, okay, going down, but still in the positive, but the amplitude or the voltage is getting lower. Okay, so that's why we are drawing here in the ECG a line that is moving downward because the voltage is getting less and less, and this drawing is proportional to the length of the projected vector. So in 1 we have a line, and in 2 it is a larger line, and also in 3 we have also a line in 3, and it's shorter than in 2. Okay, so at the second or part of second, which is 0.05 part of second, we have the last minute area of the ventricle, in the left ventricle actually, okay, that is not depolarized yet. Okay, it's not being depolarized yet. So the voltage is going to be very small, okay, and the axis of the instantaneous or the cardiac instantaneous axis is now moving, okay, to the left and up, and that's because the areas that are not polarized, depolarized, are in the base and in the left side. The base of the heart, toward the base of the heart, and to the left side because the left side of the heart is slower to depolarize. And we have seen this here too. In the ventricles, it's slower to depolarize than in the left ventricle than in the right ventricle, because it has a thicker walls, larger actually mass, so it's slower to depolarize. Okay, um, so in C actually we mentioned that the cardiac axis is slightly shifted to the left. Okay, here it's slightly shifted to the left than in the previous picture, and that's because the ventricle is slower to depolarize the left ventricle than the right ventricle. That is why the cardiac axis is now a little bit shifted toward the ventricle. Now the shift is even larger, okay, but here to the up, okay, and because the electrical actually axis is moving upward, because the base is last to be depolarized and the left base is the last part to be depolarized. So the axis has been shifting now. We move the instantaneous cardiac axis here to see how the projected lines or vectors will be actually found in the leads. So here's the instantaneous cardiac vector, and we will draw perpendicular lines on lead 1, on lead 2, and on lead 3. It's hard to see that because the axis of the cardiac axis or vector is very overlapping with the lead 3. Okay, so we will notice that the projected line in lead 1 is positive, but it's short. Okay, it's still positive, but it's short. So we are still going down. Okay, we're still going down, but still we have a positive deflection in lead 1. In lead 2, it is small, but it is in the negative, okay, because it's in the negative part of the axis. So we are having a negative or lower deflection, a negative deflection. So we are down the straight isoelectric line in the ECG. Okay, so we are in the lower part, not in the upper part, because the angle here is negative for lead 2. Okay, the projected vector in lead 2 is negative. Also, we will find that in 3, okay, it is even more negative deflection because it's overlapping with the cardiac vector. It's more on the axis of lead 3, the cardiac vector at this instant. So you will see a greater drop to the negative deflection side. Okay, so we have a positive deflection here, but it's smaller in voltage because most of the heart is now depolarized and very small area is not depolarized. Here we have negative deflection, and here we have negative deflection, but more negative deflection in lead 3, okay, because at this instant the cardiac axis is parallel to lead 3. So this is how lead 3 sees the cardiac axis at this moment. It sees this best. Okay. After complete depolarization, you will not have an instantaneous cardiac vector. Okay, you will not see a cardiac vector because we don't have differences in charges. So we will not pick up a current here. So there is at about 0.06 second, there will be no current flow, and around the heart no electrical potential is going to be generated. So we will go back to the isoelectric line, okay, for all the three leads. Okay, so here we are back to the straight line. Okay, there are no electrical potential, so no vectors in all three leads, no vectors. Okay, so now we have got the R, okay, and S. So these are the S waves, okay, and we have seen the S waves in the previous actually image, okay, when we started to have a negative deflection, and now the S is complete now in the 2 and 3, but in 1 we didn't see an S deflection. Actually we have now the R and S in lead 2, and lead 3 we have the R in lead 1. Now, what about the Q wave? We haven't seen Q wave in these three leads. Why? Q wave is actually not very commonly to be seen, and it's only seen, okay, of course, at the beginning of depolarization, when the left part of the ventricle of the ventricular septum is depolarized before the right side of the ventricular septum. At this instant, which is very short, that's why it's not always picked up. Okay, so when there is a left depolarization and no right depolarization, the vector of the heart is going to be in the negative direction, okay, like this, but for a very short time, okay, and that will give us a Q deflection that is going to be negative because it's in the negative side. Okay, it's going to be in the negative side. So that's when we see a Q deflection.